This chapter we explain about one last step of system identification process, which is model selection and model validation. In this chapter, we go over important considerations in model selection that rely on the important concept of bias and variance decomposition. These two quantities are properties of the model. They cannot be reduced small at the same times. If the model has large bias, it's going to have a smaller variance. So it's kind of a trade-off. We will go over this concept and some mathematical explanation. So the process of model selection is starting with you have many model candidates, and then you would like to pick one, and according to some criterion or according to some procedures. So the criterion we learn in this lecture is called using the model selection scores, and another approach is to use cross-validation process. So after you pick a model according to that criterion, the very last step is to perform model validation, is to check whether the model to check how the model perform on the unseen data set. So this is to test the residual error from the model to check the cross correlation between the residual and the input. All right, this is called white test and cross correlation test. So in this video clip, I think we can cover the first two concepts, and actually probably we can take a look at some examples of model selection scores and numerical examples. Okay. Let's start with considerations in model selection. Everything will rely on the concept that you want to obtain a good model, a model that has good quality, depending on your task. Is if it's a regression, you want you want the model output or y hat to approximate the actual y best. And that, of course, there's a way to measure this quality. For example, you can use MSE, mean square error. You can use log likelihood if the model is estimated from maximum likelihood principle. You can use in statistics, you can use R square and so on. You can use residual sum of square. So the quality, that's the first thing you want to take a look how the model fits your data. But the thing is, what we're gonna learn shortly is that the model quality, when you measure by MSE, these quantity always consists of two terms, two contributions, bias and variance. We're gonna learn that a complex model, think about state space equation where n is huge, where n is 100, all right? That's a complex model as compared to, you know, first or second order state space equation. So a complex model will have small bias because it's so complex. It has more degree of freedoms. It has a lot of flexibilities to adapt and to learn characteristic in the data. But it comes with a price because a complex model will also have a higher variance. This is as compared to a simple model. So when a model has higher variance, it means that the point estimate you obtain from a single run, from a single estimation, cannot be reliable in a certain degree, right? So that is what we call a trade-off between flexibility, which if the model is complex, it has high flexibility, it has small bias. but because it has higher variance, that's a drawback. So you sometimes you need to trade off between simplicity and complexity. So to take a look at flexibility, which high flexibility means that high complexity, or you want to prefer something simple, okay, something parsimonious, which means that something require only a few parameters in the model. That's the first aspect of choosing a model. The second aspect is to look at the price in terms of the effort of estimation, in terms of computational effort. All right. As you have seen when we talk about estimation method, uh, it's it sometimes it's implicitly assume a model structure in the method, right? For example, of course, subspace method uh, is applicable to state space equation, right? Or if you look at it this way, if you may put the model class as a standpoint, right? Suppose you start with this. You start with, okay, I'm going to use ARMA model, and then from this point, you may want to see, okay, what kind of estimation techniques can we apply to these model class that I want to perform system identification. You can say, I can use PEM, right? That's one thing. I can use MLE, maximum likelihood estimation, all right? So now you can, when you have applicable methods, now maybe you can take a look at each 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 estimation method and see how much effort required by those methods, and you can compare about um, algorithm complexity, because these also varies according to the method. For example, PEM requires solving nonlinear optimization as well as MLE, right? But if I say, okay, if I pick model class to be ARX, you know that model ARX can be estimated by using the simple linear regression or linear least square. What is the computational cost in linear least square as compared to PEM and MLE? You say, oh, that's simple, right? The solution of least square is the same as solving a system of linear equations. Okay, so which means when you take a look at the model choices, please keep in mind about the computational effort that that depend on the model class. And think about we can see more example on PEM as well. Remember when we talk about PEM, it requires the choice of the cost function, loss function, V. This is how you measure the covariant matrix of prediction error. The choice of the loss function can be the trace function, the dead function. All these things, all the choices, all these loss function has different properties, and also results in different computation complexities. So that's why the second consideration can be kept in mind as well when you choose model candidates. And the last one is when you're going to use the model. The purpose of using the model have some have some it requires consideration from the user point of view. For example, if the model is going to be used for prediction purpose, right? For prediction or forecasting. So what do you know about forecasting? So we're going to collect the data up to a certain time, right? But then you're going to estimate, all right, going to estimate the output of the future time. And as you have seen, the model that will be used for forecasting, for prediction, the equation would be something like yt, right? Yt hat is going to be a function of yt minus 1, because it can use only the information up to time t minus 1, right? So sometimes you can go all to the history of y, right? Something like this, which means when you use such model, you need to provide a way to cache or store the memory of these measurements. Okay. And if the model is simple, storing or caching these values are not what they are not computationally they are not a burden in terms of computation. But if things are more complex, if you use a more complex model, but to perform forecasting, so these things can be kept in mind as well. For controller design purpose, what's the different aspect that you need to aware? For controller design, when you pick a model class, stability is a very important issue, which means if your design, if the physical system is stable and you're going to use estimated model in the control design process, of course the estimated model should be stable. And then between the model, so suppose you have model candidate 1 and model candidate 2, all right? Model 1 is obtained in such a way that the estimation process, can guarantee stability, while the second model is not guaranteed. But that doesn't mean that it's unstable. It's just that the framework in the estimation, doesn't make sure that the estimated one will always be stable. In that case, when you keep this in mind, then you may have enough, have a preference on model 1 over the model 2. Okay. And then the last one, which is a very broad consideration, is depends on how you, this is how you can use model parameters or model parameters or a function of model parameters in order to infer something, to draw some pattern, to make an inference, make a conclusion. For example, if you have AR process, all right, you have AR process, you have noise, you have Y, all right, and statistically, we can say that, not we can say that there's a relationship that everyone know that the spectrum of the AR process, all right, is a quadratic function in the AR polynomial. Okay, let me sketch in this way. This A is this AR polynomial that contains AR matrices. Okay. Spectral density of a random process has a connection with the conditional independence property. This is how you can explain the relationship among the variables. For example, there can be if the inverse spectrum at the ij location is 0, it means that the corresponding yi and yj are conditionally independent given other components. So this is an example of inference problem, because once you estimate AR model parameters, you don't actually use model parameter, or you don't use AR model for regression purpose. You actually use it. You actually use the model parameter to calculate some function of model parameter. Here, some function means that you calculate inverse spectrum. And the zero pattern in the inverse spectrum statistically explain conditional independence between a pair, between the component yi and yj. Yi and yj are basically components in your yt, right? Yt is a random process that you use AR model to explain its behavior. So this is an example of model inference. Okay, so if you have that purpose that, okay, I'm going to use AR model for computing the spectrum inverse, then other issues come in place, because, for example, the spectrum is only defined for stationary process, right? And how stationarity defined in terms of model parameters. So that connection will be taken into account in back into your estimation process, and back into your choice of model as well. Okay. So this is the general way for you to aware that, okay, when you choose a model, you have to consider all of these aspects. So let me move to another topic. As I mentioned first, that when we talk about the most important aspect, which is the model quality, the simple message is you just don't look at the MSE itself alone as a number. It's important to know that this MSE has three parts, three contributions. So let me explain the concept first. We start with the regression model, but can be in a nonlinear way. Your response y is related to predictor features input x, okay, by some nonlinear function. In general, your f can be linear regression, can be nonlinear, can be, for example, neural network, right? It can be a function of trees, any kind of models, right? This model is called linear additive noise, because it says that your y is actually a function of x. It is related by, their relationship is explained by y, but there's a noise corrupted in this model in a linear way, plus nu. This nu is model to have zero mean and variance of sigma square. Okay, if you take a look at the last equation, you will see that the MSE can be decomposed into three parts. Okay, that's what we okay. This is MSE when we perform a regression model. What we're gonna do is we want to propose, right? When we want to propose f hat. Okay, this is DGP. You're gonna come up with f hat, which is your model, and once you use the model to estimate y at the value x equal x0. Okay, so the MSE, right? So mean square error. So it looks at the error, so it's y, the actual y subtracted by y hat square, right? And in this equation, I use y and x as capitals. to keep in mind that these are random variables. So whenever you measure the data, you measure the measure the input x as a value x0, then you take a look at the MSE by taking the expectation. Okay, so y minus f hat x0 is going to be, you use this equation, right? Plus noise. Okay, so when you make a square, and then so when you take the expectation, what do you get? So it can be decomposed into 3 parts. We will show it soon, but let's take a look first. So this expectation, when you make the square and the expectation, it can be decomposed in 3 terms. The first term is the noise variance, sigma square. The second term says that expectation of f hat at x0, okay, minus f of x0. F of x, okay, is, I mean, f is the true relationship between y and x. Okay, so it's a deterministic function, but it's just the input x can be random, right? So this is the mean of your output, right? The mean of your output. Why your f hat is random? Because your f hat depends on what? Think about your model. Your model typically, when you talk about model, for example, this is your linear model, right? Your model depends on the parameter, but usually your parameter depends on y. The way you compute what the beta hat is, of course, you're going to use the data, right? So as I said several times, that model parameters, when you estimate it, typically model parameter is a random variable because it is an estimator. That's why generally we treat f hat as random. So this is the mean of your model output. You compare it with the actual relationship, which is actual f. You make a square, right? So this is bias square. All right, bias square. The third term is what? Is to look at your model output y hat, subtract by its mean. Subtract by its mean, you make a square and then take the expectation. That is the variance. Okay, so we give you the final results first. That we're gonna prove shortly. But these say your MSE always, you can break your MSE into 3 parts. The first part cannot be manipulated. It's always there as long as your actual y comes from linear additive noise model. If the noise corrupt in the equation has a high variance, your MSE will always have this portion. The second term is the bias term. Of course, bias square. Everything has to be sum up to MSE, which is non-negative. Okay. This is basically tells how your model output accurately predict the actual y, the actual f, right? That's the bias. The third is the variance. This is the fluctuation in your model output. This is the important decomposition called bias-variance decomposition. And the thing is, we will see by some illustrative example, some mathematical proof, that if you make the model more complex, your model is f hat. If you choose a complex model, you can bring the bias down, but the variance be up. So there's a trade-off between these two quantities. You cannot make the both terms small at the same time. Okay. Okay, here's the proof. Let's see. The proof of bias variant decomposition. Oh, let me go back to one important thing. Totok, can you find a perfect estimation method? Can you propose a model or propose estimation technique that can bring MSE down to 0?
No, Achan.
Why?
Because always there is variance sigma square.
Yes, very good. Please keep in mind this is called a reducible error as long as your y come from linear additive noise model, you cannot make MSE 0. In your simulation, in your experimental results, if you have MSE very arbitrarily small to 0, it means that something in your experiment has to be checked, because theoretically it's not possible. It's possible if what? If your y come from noiseless model, right? If everything is noiseless, and if you pick f hat that are actually perfectly as the actual f, that means it's possible to make 0 MSE. But that's not realistic, right? Not realistic. In real data set, data are I mean, realistically model as you know, as noise corrupted model. So as I said several times, that MSE cannot be that small, cannot be 0. Okay. Okay, now we take a look at the bias variant decomposition. We make assumption that the true deterministic, the true representation of the relationship F is deterministic. Okay. Secondly, the variance of y given x. Okay, when x is given, this term is deterministic, right? So the variance of y would be the same as the variance of noise, which is sigma square. Okay. When you take the conditional mean EY given X, okay, because the noise here is 0, conditional mean of Y given X is of course Fx. Okay, that's one thing. Your F hat is random, as I mentioned previously. Your F hat, here I didn't say things clearly, but your F hat always parameterized by some model oh, it doesn't. Okay, just now. Your F hat is parameterized by model parameter, but this one in your estimation process, your theta is calculated from data, which means your theta is random. When your theta is random, your F hat is random. Okay, so in the following analysis, actually, it's going to be the analysis when the variable x is given by a value, all right? When your predictor, when your feature x is evaluated as some deterministic value as you measure from the sensor. So but we omit that notation. Okay, first we take a look at MSE, right? MSE is what? The mean square. Okay, so mean square error. We observe the error and then square it. Okay, and then what we do is to just expand the square. Everyone knows, right? Just expand the square. And the next thing is to use what? To use that the expectation of the second moment is the variance plus the mean square. Okay, and the same for this term. Hold on. This is right. The second moment, right? The second moment of f hat which is everyone know this, right? Expectation of y square is what? Variance of y plus e of y square, right? That's the basic thing in the variance, the second moment and the variance. Okay, so the green term, that's the second moment of y hat, right? So it's gonna be its variance plus its mean square. So the the last term, expectation of 2y here, y is fx plus new, right? Expectation of y times fx, okay, that's gonna be what? It means that here, it means that it's a conditional mean when x equals small x, all right? So your y is going to be e of y, which is fx, and e of f hat, which is e of f hat. Okay, and next. Let's see. The next term is the the yellow term, the expectation of y square, right? This term goes away to the yellow term. Y square is if f hat square. This is the deterministic term. Okay, e of y, right, is what from here? E of y is f hat. As we see, the noise has zero means. And the last term, I mean the the remaining term, just follow the same way. Okay. The variance of y plus fx square is what? Is sigma square. and take a look at now. Take a look at these terms. Take a look at the. We take a look at these terms, and of course, we take a look at these together. Okay. All right. Everyone just follow. Variance of y and variance of f hat is variance of y, variance of f hat is this yellow term, but the term in the what? In the red box that I just highlight is what? It can be combined. It can be combined and complete the square. Right? You can complete the square into fx square, expectation of f hat square, and the cross term. Okay. Now you recognize, now once at this part, you recognize that fx is deterministic, right? So you can also write fx as e of fx as well, because it's deterministic. And then you take the expectation out of the bracket. So this term becomes expectation between f and f hat, and everything square. All right. And the last one, that is how you can show that it is irreducible error, which is the noise variance. It is the variance of f hat, and the last one is what? The bias of f hat square. Okay, so that's how you show the bias variance decomposition. Now we're gonna apply this concept and see it explicitly what it means, and what you're gonna see when you use different degrees of model complexity. So I'm gonna use an example from a linear model, because the analysis is simple. Okay, suppose you have two nested linear regression models, M1 and M2. Okay, I model in this way, model 1, y equal x beta. That means I put x1, x2, dot, 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 xn. Suppose I have n predictors in the model 1. Okay. In model 2, I also include these predictors in the model, but I put another predictor, x tilde, okay, in the second model. So the second model, of course, is more complex than the first one. Okay, these models are nested because it means that if you partition your model 2, you partition the coefficients of model 2 into x and alpha, right? And this guy is called gamma. Actually, this beta has the same meaning as beta in the first model because it's explained it is the coefficients of the first predictors, the first group of predictors. Okay. When alpha is 0, of course, your model 2 reduces to model 1. That's why we call these two models are nested. Model 1 is nested in model 2 because model 1 is a special case of model 2 when alpha is 0. Okay. I write it in this way, but I use the matrix notation that this guy, the regressor of model 2 is Z, all right? The regression coefficient is gamma. But keep in mind that the first block of gamma, first portion of gamma, has the same meaning as beta in model 1. Okay. So we would like to compare these two models in three following aspects. And I state the results first before we prove it. First, model M2 has a lower MSE in predicting Y than model 1. Does it make sense? When you use these two models to predict Y, M2, which is a more complex model, results in lower MSE. That's kind of intuitive, right? And yes, that's the fact. All right. But the second bullet says, on the other hand, even though M2 seems to be more beneficial than M1, but the covariance of beta hat in M2 is bigger than the covariance of beta in M1. The second consideration should be discussed with care because model M1 is bigger. It has more parameters. What I compare is only the portion of beta. All right, it's only the portion of regression coefficients associated with the first group of predictor with X. Ping, when you have a bigger covariance, is a favorable thing? Is this a good thing or undesirable?
With bigger covering is not a good thing.
This is unfavorable, right? So now when we see that the second bullet, of course, it seems that M2 has a drawback in this sense. The third bullet, all right. Even though the M2 can have lower MSE in predicting Y, but the variance of Y hat from M2 is higher than the variance of Y hat from M1. Okay. The second, number 2 and number 3 are different by this matter. Number 2 measure the variance of beta hat estimator. Number 3 measure the variance in the prediction. Okay, So number 2 and number 3 are disadvantage of using more complex model. Okay. We prove, okay, everything. And so we're going to use subscript 1 for model 1. Everything labeled with 2 will be for model 2. All right. And in order to show this, we will rely on the linear algebra results, inverse of block matrices. Suppose you have a block matrix that can be partitioned in this way, A, B, C, D, that is bigger than 0. And this matrix has a Chu complement on the 2, 2 block given by this. Okay, please review the Chu complement. Okay. So we have the result that f x is bigger than 0, even only if the Chu complement is positive semi-definite and A is positive definite. Okay. The results of the inverse of block matrices says that when X is inverse, each block has inverse in this way. And it involves a lot of Chu complement in the expression. Okay, as you see here. One fact that I want you to verify is not difficult, just verify it from here, is that if I have a quadratic form, UV, all right, where, okay, now I restrict down to the case that my X is symmetric. When my X is symmetric, this C part is actually B transpose, right? This is a quadratic form of inverse in X. And if I subtract it by U transpose A inverse, the 1, 1 block inverse, it can be nicely expressed as another quadratic form. I mean, you calculate everything, rearrange, right? It can be represented by another quadratic form, right? This quadratic form is parameterized by S inverse, Chu complement of X. But from the results previously that I say, if X is positive definite matrix, its Chu complement is also positive definite matrix, which means your S inverse is also positive definite matrix. That will give an important result that this quadratic term is also positive semi-definite because of the non-negative in the Chu complement. Okay, this result is very important. This guy positive, right? This guy is also positive because A inverse has to be positive by this assumption. But then the subtraction of 2 non-negative terms, generally are not guaranteed to be positive, right? Like you have 6 minus 10, right? They are both non-negative. You subtract it, you don't know in general, but this just says that the results of this subtraction is also still non-negative. And we will use these results a lot shortly. Okay, I'm going to prove one by one. I'm going to prove the first one. The MSE of the complex model, MSE in predicting Y is lower than MSE of simple model. Okay, that's a typo. MSE of model 2 is smaller than MSE of model 1. Okay. Remember, because we give example of linear regression model. Remember the concept of linear regression model. You have you want to estimate Y and you project Y onto what? If you use the model, linear model, you project Y on the range space of X. Okay, and your p hat y can be illustrated as a projection of y by using this matrix P. What is the matrix P? From the linear regression, Napat?
It's a orthogonal projection matrix.
Yes. Do you recall its expression? From linear regression. Linear regression, Napat, what is your beta hat?
X transpose X inverse X transpose Y.
Okay, City Park, when you do the projection, when you do the the estimation, right? You multiply. What do you do with beta hat?
Multiply with X.
City Park multiply.
X multiply with X transpose X inverse and X transpose Y.
Okay, so talk, what is your projection, orthogonal projection matrix?
X times X transpose X inverse X transpose.
Yes, so this is the matrix P, all right, orthogonal projection. Okay, so if you use different regressors, then you have different orthogonal projections, and it's not hard to see that when you compute MSE, which is basically you wanna you need to compute y and y hat, right? Norm square, right? MSE, and then these can be simplified. Just expand and simplify. You would see that MSE is given by these yellow terms. Okay, it actually depends on the orthogonal projection matrix. And of course, orthogonal projection metric depends on the regressor matrix. All right. So I use the notation P1 and P2 for model 1 and model 2. Model 1 use X as a regressor. Model 2 use Z as a regressor. But the regressor Z also include X in the first portion. Okay. Now, when you see the MSE in this way, the first term is constant because it depends on the data. Now you need to compare only the quadratic form in Y using orthogonal projection matrix. Then you only need to see that this quadratic form, Y transpose P2Y, is bigger than this one. Okay, to show, if you can show this, MSE2 is less than MSE1. Okay, and to show this green term is quadratic, right? So we're gonna show it by this instead, P2 minus P1. We're gonna examine this property, this quantity. So basically, you need to compare if matrix P2 is what is bigger than the matrix P1. Okay, now we're going to use that orthogonal projection matrix is given by is actually given by, depends on the regressor matrix. For P2 I use Z. Okay, but because the relationship between Z and X from the green term, okay, then you just put Z, you just put here. And for P1, because P1 is for model 1, it uses X as a regressor. So P1 is given by this expression. Now, the part that we want to show that P2 minus P1 is bigger than 0. Okay. Can you see that this term is actually what? This X, right? And X transpose is actually this guy and this guy. All right. And X transpose X inverse is actually just the one block in this matrix, in this ping matrix. So it fits into the framework that we have this result. Okay. You have quadratic form in U and V, right? You have quadratic form, and then you subtract it by another quadratic form parameterized by A inverse, the one block. So I'm going to leave this as an exercise. I think it's not hard because we just apply this result. Okay. So P1, as you see here, is P1 is another quadratic form using X transpose, using X transpose X inverse, which is the 1 portion here. The results of the subtraction compared to this one, as I mentioned, is going to be another quadratic function parameterized by true complement inverse. What is the true complement in this example? Is going to be this matrix minus this matrix times this matrix inverse times this. Okay, and because this matrix, the matrix in the pink term, okay, is this matrix positive semi-definite or not? I must say positive definite. Is it positive definite, the pink one? Pink. You're not here? Total.
Yes, อาจารย์
Because
quadratic form.
yes, because this matrix is actually Z transpose Z, right? And I mean, with the notation here, you already assume that it's positive definite, right? So which means if the matrix in the pink term is positive definite, its true complement is also positive definite matrix. When S is positive definite, this inverse is also definite, positive definite. And that's why the result is non-negative. Okay, so you have shown that P1 is bigger, P2 is bigger than P1, and that makes MSE2 smaller than MSE1. Okay, now the next results. Okay, even though model 2 has a lower MSE, but its estimator beta 2 has bigger covariance. Okay, again, as I mentioned, beta, we only compare beta. We don't compare gamma, the whole regressor, because the whole regression coefficients, because M2 has more parameters than M1. We only compare the corresponding regression coefficients. Okay. Again, this is model M1. This is model. This is model M2, right? We call it gamma. So basically, covariance of gamma would have two portions. I mean, it can be partitioned as the 1 block would be covariance of beta, right? The 2 component would be covariance of ping. Ping.
Yes, John.
What is it? Napat.
Covariance of alpha.
Covariance of alpha. Total 1, 2 block.
Cross covariance between beta and alpha.
Cross covariance. Okay, everyone know. So basically, we're going to extract the 1 block from covariance of gamma, right? So this is the 1 block. Covariance of beta hat 2 is actually the 1 block of covariance of gamma. Okay, and recall the result from least square, from linear least square, is that when you have a linear regression model, all right, when the noise is homoscedastic, the variance is sigma square. After you perform the estimation and everything, it can be proved that the covariance of beta hat is sigma square x transpose x sigma in x transpose x inverse. This is what we've seen in the lecture of linear least square. So I'm just saying that, okay, we can say that the covariance of beta 1 hat is what? X transpose X inverse. So just control the noise covariance to be unit or some constant. For model 2, the covariance of gamma hat would be Z transpose Z inverse. Okay, but then, so Z transpose Z inverse is this matrix. But then we need to extract what? Because we just say that covariance of beta 1 hat is a leading 1 block of this guy, right? So after the inverse, we're going to take 1 block. Then we use this result. The inverse of block matrix. After you make the inverse, all right? After you make the inverse, we're going to extract the 1 block, right? 1 block. So that's why, okay, we take a look at the yellow term as a partition of 2 by 2 blocks. And then after the inverse, the 1 block has this expression. Okay. What is A in this slide, City Park?
A is X transpose X.
A is X transpose X, right? What is B, Toto?
X transpose X tilde.
Okay. What is D, Ping?
D HTD transpose HTD.
Huh? Say it again.
HTD transpose HTD.
Okay. All right. So everyone follow this, okay? We use the result from the inverse of block matrix. Now what do? We want to show that covariance of beta hat 2 is bigger than covariance of beta hat 1. Covariance of beta hat 2 is what? Is the 1 block, right? What is covariance of beta hat 1 is X transpose X inverse. And that is what? That is our
A inverse.
A inverse. Okay? So when you want to compare it to, if one matrix is bigger than another one, you just compute the difference and claim and examine if it's positive semi-definite, right? So I subtract covariance of beta 1 hat from covariance of beta 2 hat, which is very simple. This is what we read from the 1 block, and covariance of beta hat 1 is basically A inverse. And the results of subtraction is actually this. All right, the guy in the red box. And what about this guy? What do we know about this term? Is this matrix positive semi-definite?
Yes.
If it is, why? Why?
Because A inverse is positive definite and it's this term in quadratic form.
Yes. All right. You recognize that, oh, this is quadratic form, right? This is the green thing transpose, right? And parameterized by S inverse, which is positive definite. Then that's the result. Okay. This is once again, I emphasize that this is covariant in the estimator. Which means the coefficients you estimate from complex model, when you take a look at its point estimate, calculated from one data set, one realization, it is less reliable than the coefficient obtained from a simple model because it has higher covariance. The last one, the second one is the variance of estimator. But the variance of estimator also and certainly have effects on the variance of predictions, right? Think about a general expression like when you do the prediction, you're gonna use f hat is some function of x, right? But your model is always what? Parameterized by model parameter. Your f hat is neural network. Your theta hat is the weight, right? So if theta hat has high variance, you take a look at y hat as, I mean, again, your f hat is random because theta hat is random. You think of y hat as a random entity, and the variance of y hat also depends on the variance of theta hat. But how? In what way? In a nonlinear way, because it seems like y hat is a nonlinear transformation of your theta hat. Okay, so in general terms, probably you cannot tell the degree of the relationship between variance of y hat and the variance of theta hat. But in a linear model, we will illustrate it this way. Very simple. Okay. So think about again, you have this notation, you have linear regression model. Remember that this is a vector form, right? This is a vector form. This is a vector form for performing the training or the estimation. If I take a look at this as an equation to explain variable, like if I only have one row, one instance, one example of a data set, one sample, right? I would write it in this way, y equal x transpose beta, okay, which is x1 beta 1 dot xn beta n. Okay, so this is a vector form we use to explain the estimation process. Okay, different rows in y and in x is just different samples of data. Okay, now I want to explain it this way that, okay, suppose you have the estimator beta hat, and for the second model you have a gamma hat. When you do the estimation, assume, let's just say that you have another sample of predictor, just one row. So that row is given by U for model M1. For model M2, that row given by W. But because M2 includes the model M1, which means W must be what? Must contain U as well, right? Contain the predictor of the model model M1. Okay. So we're going to compute the variance for y equals U transpose beta. Of course, the variance of y1 hat, this is linear in beta hat, right? This is linear. So variance is going to be U transpose, right? Covariance of beta hat and U. Okay, variance of y2 hat is going to be what? It's going to be W transpose covariance of gamma hat times W, because y hat is linear in beta hat. Okay. Now you substitute, because covariance of gamma hat. What is the covariance of gamma hat? Is Z transpose Z inverse, right? This is the expression. Covariance of beta hat is X transpose X inverse. Now again, it looks a very similar form to the result on page on the inverse of block matrices. This is quadratic form, right? This is quadratic form subtracted by quadratic form in U. And the matrix that parameterized here is actually the 1-1 block of this bigger matrix. So if you compare to the results here, it fit the same form. And the results of the subtraction, as we see on this slide, the result of the subtraction is always non-negative. Okay, non-negative, which means variance of y2 hat is bigger than the variance of y1 hat. All right, that's conclude the result. Certainly, complex model has lower MSE, but has higher variance in the estimator and in the prediction. That's the concluding message. So we have a few minutes left. So that's why when we compare model with different degrees of flexibility, I think this diagram is useful. If we take a look at two aspects, flexibility of the model, which is the same as, of course, the model that is more complex would have more flexibilities. It has more degree of freedom to adapt, right? If we look at the y-axis, this is in terms of interpretability. Okay, what it means, I will explain it here. Now let's take about like restrictive linear model. Like think about lasso solution. What is the behavior or the important characteristic of the lasso solution? Napat?
Sparse.
Beta is sparse, right? Linear regression, beta is sparse. When beta is sparse, we say that this is restricted solution because some entry are restricted to be 0. It has less flexibility because the parameters are shrunken down to 0 in many entries, right? Okay, in that case, the model has less flexibility, but high interpretability because the 0 pattern in beta, I must say, because the non-zero pattern of beta would explain which predictors, which variables are significant in your model, right? Because at the 0 location, like it basically means x1 has no effect on predicting y, but x3, x4, and so on are important. All right, so this is an example. The lasso solution has less flexibility, but its solution reveal or can explain some meaningful information of your model. High interpretability. What about a very complex one, neural network, deep learning models? It has more flexibility, right? What about in terms of interpretations? Napat, if we just print all the weight values of the deep learning models, what can we see? What can we say about those values of weights? Napat. And no one ever printed. Yeah, no one ever printed, right? It's like I explain or can in Thai.
เหมือนมันบอกอะไรไม่ค่อยได้ครับเพราะมันพารามิเตอร์มันเยอะมากแล้วมันโยงกัน
Yeah, right? A huge number of parameters, the weight in the neural network. Can you say something about the weight in one layer, the relationship of weight in one layer to the weight in another layer? No, right? No. Even you apply dropout, you know, some weights are 0. But it's just that it's so complicated in the model structure that those patterns cannot give you some meaningful or some compact information about you know relationship between input and the target. So the complex model has less degree of interpretability in this sense. Okay, and of course there are gonna be some way in between, right? Generalized additive model. This one we haven't seen it in the class, but it is actually non-linear models, but it is still structured in some sense that it can still in between. It's not as complex as neural network or any like general non-linear model, but it's more general than linear one, so more complex, but still you can interpret something from the structure of estimator in GLM. Okay. All right. So this scheme we would just would like to explain and conclude the concept of bias and variance. The red one is the model space. Okay. Model space. Suppose this is the point where you obtain your parameter estimate. That estimate is going to be different from the truth one, right? And that is how you measure the bias. The circle represents its variance. Okay. The green zone is called restricted model space. For example, linear model space is linear. Restricted model may be something like you say, oh, you restrict the coefficient to be 0. Restricted. Okay, so the estimator you obtain here, the green one, will have another bias. Like compared to the red one, that bias is from estimation bias. Because you restrict, you put more constraint in the parameter. But the circle, which represent the variance of restricted parameter would be less than, right? Less than the variance of the red one. The red one is without the restriction. So this is to basically illustrate the trade-off between the bias and the variance. Which one between the red, the green one, which one represent a simple model? Which one represent a complex model? Total?
Simple model is restricted model and complex model is, for example, the red one.
Okay, yes, very good. That's the conclusion. All right. Okay, we end the lecture here. Just see you on Wednesday, and again your term project. And I hope that I should finish the lecture next week, because you will use it for term project as well. Okay. Is there any questions?